Hello everyone, welcome back to our lecture on solutions to climate change and different ways of approaching how to reduce the amount of carbon dioxide in the atmosphere. We just talked about carbon sequestration. Now we're going to cover concepts of geoengineering. Geoengineering is the idea of doing large-scale engineering projects in order to drastically change our environment in order to produce some effect. In this instance, reduce the amount of global warming going on. So one of the ways that has been proposed of doing this is cloud seeding. So we talked about cloud seeding early on in the semester, but it's the idea of inputting a large amount of water vapor, salt crystals, silver iodine, some particle into the atmosphere in order to provide cloud nuclei and increase the cloud cover over the ocean. And as you do that, you tend to increase the albedo of the ocean. Ocean water tends to have a very low albedo, as all water does, whereas clouds have a very high albedo, bright white color. And so if you can increase the amount of clouds over the ocean, then you can decrease the amount of solar energy hitting the Earth and therefore reduce the amount of climate change going on. One of the downfalls of this is that we really don't know how big of an impact it can be, and a lot of estimates suggest that it would be extremely costly, more costly than other methods. And so one of the downfalls of a lot of geoengineering projects is both the extreme cost as well as the fragile state that it kind of puts the world in. Because if for any instance that the geoengineering project was to have to shut down, it might spiral the climate back to a scenario of extreme emissions, back to what they would have been. So we always have to be careful of that when conceiving of geoengineering projects, and it's one of the reasons why a lot of them have not gone past the preliminary stages. Another one that has had a little bit more traction, at least in the research community, is stratospheric aerosol solar reduction. So this is the use of sulfur dioxide gas in the upper atmosphere in order to reduce the absorption of solar radiation. So just as with cloud seeding, you're producing a large amount of high albedo substance in the atmosphere, and that reflects light away from the Earth, as you can see here, and reduces the amount of warming going on. This is the same thing that a volcano might do by pumping out a huge amount of sulfur dioxide gas into the stratosphere. Remember, that's the second layer above the troposphere. Then a volcano tends to reduce the temperature of the Earth, at least temporarily, until those aerosols fall out. But there's definitely some downsides to this as well as upsides. So you can see here, these are climate model simulations that show a business as usual climate scenario and how much warming we would expect. And this is a scenario using the same emissions of CO2, but implementing stratospheric aerosols in order to help reduce the temperature. And so you can see here that it pretty much completely eliminates the amount of warming due to CO2 and actually causes some global cooling. And so it would be effective, at least for that time being. But while it's theoretically possible, it puts the environment in an extremely unstable situation. If at any point we were to reduce the amount of sulfur dioxide we put into the atmosphere, we could shuttle right back into this extreme warm scenario. And the Earth really has no precedence for that extremely rapid change in climate, and could cause some really extreme environmental effects, ecological effects, as well as health effects. Additionally, you would just have a lot of aesthetic problems as well. By pumping a whole bunch of sulfur dioxide into the stratosphere, you probably won't see stars at night anymore. And you might have a lot of other issues with how much pollution is required to actually get these aerosols into the atmosphere. So it's definitely not just something that's currently taken all that seriously, but it's a fun thought experiment, at least at the moment, for ways that we can address this problem. Another potential solution that might help is the use of glacial artificial sills. So, as we talked about in the last lecture, marine terminating glaciers can have a significant amount of melting due to the influx of warm ocean water to their terminus. As the water laps against the end of the glacier, it can provide heat to induce more melting. And so if we have a way of reducing the amount of warm, deep water from reaching the glacier, then we can reduce the amount of melting and therefore reduce the amount of sea level rise. And one way to potentially do that is by setting up an artificial still. That's creating an underwater seawall that would help prevent that warm water from reaching the glacier. That warm water doesn't like to move up into this upper area, and instead likes to move along the bottom of the ocean. And so if we put up a wall, we might reduce the amount of influx of that heat. This, of course, would be extremely expensive and would be a huge engineering project in some of the coldest and most remote places on Earth. And so it's basically just a concept at this point right now. A more feasible solution might be iron fertilization. So in the Arctic Ocean especially, a lot of the plankton that live there, and the phytoplankton, are iron limited, which means that they have plenty of nutrients, all besides iron. And if you add iron to the water, then there can be huge amount of algal blooms and a huge increase in primary productivity. And so when you have a whole huge influx of bacteria that are then absorbing CO2 and causing more cycling of that CO2 into the ecosystem, then it's no longer in the atmosphere and can sink down to the ocean floor. So the idea is you spray a bunch of iron-rich water over the ocean, in the Arctic Ocean, or the Antarctic Ocean especially, and the phytoplankton would bloom and sink that carbon dioxide into the atmosphere. The real concern here is we don't really know how effective it would be, how much these phytoplankton would respond, and what kind of ecological impacts there would be with these gigantic phytoplankton blooms. So it would most likely be a small impact and potentially large impacts on the marine life there. And then the last one that we're going to be talking about are artificial sea ice. So this is definitely a promising form of geoengineering, and this is a way of increasing the amount of sea ice, particularly in the Arctic. So remember, sea ice has a very high albedo. It reflects a lot of light compared to ocean water, which absorbs a lot of light. And so if you can increase the amount of sea ice, then you're increasing the amount of high albedo surfaces, and therefore you're increasing the amount of sunlight that's reflected back to space instead of being absorbed by the Earth. And so the way that this is done, two different ways. One being you set up a machine that can pump water onto the top of sea ice during the winter time, usually powered by wind of some kind. And when you pump water onto the top of the sea ice in winter, that water then freezes and can help build up that sea ice thickness during the winter time so that it's thick enough that it won't melt away in the summer. Additionally, you can spray a bunch of white sand on top of the sea ice. That white sand is a brighter color than the sea ice itself, and that can help build up the sea ice in winter and help reduce the amount of melting that goes on in the summertime. And we can use climate models to assess how impactful this would be. And we can see here that implementing this on a large scale could potentially increase sea ice thickness in some areas by over a meter, which is definitely significant. But also, this would likely be extremely expensive, and it's not quite clear how marine life would be impacted or how much of an impact it would have on total global warming effects. So how much energy production has to change? How much does it have to change? How much do we have to change the energy sector in order to meet the IPCC goals of 1.5 degrees Celsius? And so it's an important question to make sure that we know what we're aiming for. And so what the IPCC has recommended is that in order to meet these goals, we have to convert 70 to 85% of our total electricity production to renewable sources by 2050. So that's definitely a significant amount. And the remaining 15 to 30% will be taken up both by nuclear power as well as carbon sequestration, which we talked about just now previously. And so in order to do this, the estimated cost would be around $2.4 trillion per year. And so remember when we talked about previously, unabated climate change by 2100 would cost the US alone $2 trillion per year. So the fact that this would be significantly smaller price tag for the entire world if we actually start ramping up renewable energy supplies. Additionally, it's a whole lot cheaper to start producing energy from renewable sources than the, remember, $3 to $7 trillion that was mentioned in the previous video that would be required for only relying on carbon sequestration to supply that fuel. So really ramping up both wind and solar is the most economically viable option that we have in order to meet these goals. And we can see here that in order to meet these goals, we would have to continue this trend of increase in solar power production until it's significantly higher than current coal and natural gas production, as well as continue increasing the amount of wind energy that we're producing, and slight increases in hydropower as well. So we can see in this table, by 2050, we'd have to reduce the amount of coal production by 75%, oil production by 60%, and increase non-biomass renewables by over 500%. So that's a huge increase in production, but it's really kind of the best option that we have, and it's definitely within our capacity as a society in order to reach that type of production. So what are some other solutions that we can use to incentivize this change? So one of those is carbon pricing. So carbon pricing are market-based strategies in order to reduce carbon emissions. You may have heard of a carbon tax or a cap and trade program. Those are the two types of carbon pricings that fit under this umbrella. And these are definitely not new ideas. So carbon taxes and carbon sequestration policies have been enacted since the early 1990s and have really taken off. So that in the 2005, you had the EU enacting carbon pricing. And then since then, you've had a huge increase in the number of countries that have enacted policies to put a price on carbon. And so now around 13% of all carbon emissions are taxed in some way. And so it's definitely a good start, but definitely not all that's needed at this point. So what are the difference between these two types of policies, carbon tax and cap and trade? So a carbon tax is just a flat tax on however much carbon you're emitting. For example, if you're emitting a ton of carbon, a metric ton of carbon into the atmosphere, then you're being charged by the government some flat rate, such as $50. On the other hand, cap and trade, the government is setting a cap for the total amount of emissions that they want to happen, and then they give out vouchers to companies that are emitting carbon, and those companies can reduce their emissions and sell those vouchers in order to make money, or if they emit more, they have to buy those vouchers in order to set a limit to the amount of carbon that's entering the atmosphere. And both these policies have pros and cons that we'll get into, but you can see here that cap and trade programs have the benefit of having emissions levels set by the government, and the downside perhaps of having the price based on the market for whatever these companies consider the value of these vouchers. Whereas carbon taxes, the amount of emissions is set by the market, and the price of that carbon is set by the government, who decides what that flat rate will be. In the US, you can see here that there are several states that already have cap and trade or carbon tax policies in the books, especially here in the Northeast, as well as California, and several states also that are considering these types of programs. So what are some of the pros and cons? So in terms of cap and trade, the pros are that it creates a new kind of industry or business for trading these carbon credits or vouchers. And so you can have companies that explicitly have the goal of just reducing the amount of carbon in the atmosphere, and they can make money by selling those vouchers as a result. Additionally, the amount of carbon emissions is a little bit more certain than for carbon tax, although there's a number of good examples for how much the emissions reduction would be for a carbon tax. But by setting a cap, you have it a little bit more certain. But the downside is that cap and trade programs can be very difficult to administer. They have a large overhead because you need a large government agency in order to enforce these concepts. And you can have a lot of leakages from unregulated industries, people that don't report the amount of emissions that they're releasing into the atmosphere. And so in effect, it's a cost to the government, and a lot of times those costs can be passed to the consumer, which is never a great idea. On the other hand, carbon taxes can be a little bit easier to administer. It's just a flat rate that the government is applying. They're a source of revenue for the government. That money that's being taxed is going towards the government, so the government is usually pretty happy about it. And there's more stable energy prices for the consumer because the industry knows exactly how much those carbon taxes are going to be. The downside being that it can slow business if you're implementing a tax. You have less certain emission reductions because you don't know how much the market is going to reply to this, and it taxes consumers. Again, you have more cost to the consumer. But there is a third option, which can be, in a lot of ways, a whole lot better with a whole lot less cons. And that's carbon tax and dividend. This is the idea that you set up a carbon tax, just like previously, where you're putting a price on a ton of carbon, but instead of giving that money to the government, you're giving it out to the citizens as a dividend on their tax returns. And so the benefit of this is that you have it promotes economic growth. You have a dividend or money given to the citizens that they can go spend on different industries. It causes significant emissions reductions, has a pretty low overhead. It's just pretty much an IRS form that needs to be filled out. And most of those dividends completely outweigh the costs. So over 2/3 of households would actually gain money instead of losing it. And a lot of those gains go to lower income houses instead of the higher income houses that are using a lot of carbon. How effective are these measures? In a few words, pretty effective. We can see here, these are the expected emissions under current policies, and these are the expected emissions under a $50 per ton carbon tax. And you can see that there's over a 40% reduction from 2005 levels of the amount of carbon that's released. That's over 2 billion metric tons. So it's a lot of carbon just by implementing this policy. We can also see that the amount of carbon that's no longer emitted really depends on the price of that carbon tax, what the cost per ton of carbon is. And the more expensive the carbon tax, the more industry is incentivized to change their policies, and the more emissions are going to be reduced. We can see here, for example, by 2030, if we have a carbon tax of $14, we're reducing our amount of carbon by around 600 million metric tons, whereas if we have a carbon tax of $50 per ton, then we'd reduce our amount of carbon reduction by around 1,300 or 1.3 billion metric tons. So the price has a big impact. And we can see here how that would affect the different industries that produce our electricity. By implementing a $15 carbon tax, for example, we'd reduce the amount of coal production by 22%. And a lot of that would be taken up by increases in nuclear power production and natural gas production. And if we had a $25 carbon tax, then we'd pretty much eliminate the amount of coal that we're using, and those would instead be taken up by more renewable sources and cleaner sources. So next, we'll talk about energy subsidies. So energy subsidies are a sum of money given to an energy company by the government in order to reduce the price of that energy. And unfortunately, a lot of the energy subsidies have been given to fossil fuel industries, such as oil and natural gas. and that has artificially reduced the cost of those energy sources, as well as made a lot of energy products and mining goals more economically feasible. And we can see here in this graph that the amount of money going to non-renewable energy subsidies is quite significant. In 2010, the amount of energy subsidies going to fossil fuel industries was over $22 billion. All energy subsidies have since decreased, but still the amount of energy subsidies going to fossil fuel industries is close to $9 billion per year. So it's a lot of money that's just going from taxpayers to these energy companies. So globally, we can see that over $50 billion is spent for non-renewable energy subsidies. And so this is a lot of money that helps reduce the cost of fossil fuels and make it so that they're more economical. We can see here how those energy subsidies have changed from year to year in terms of billions of dollars. We had a peak in energy subsidies to coal, gas, and oil in 2012, and it has since decreased, but it's still in the order of several dozen billion or several hundred billions of dollars per year. So it's definitely significant. Where are most of these subsidies being spent? There's a large amount being spent in the United States in terms of dollar value, but in terms of the percentage rate for the reducing the cost of that energy production, most of those subsidies are spent in oil-producing countries such as Iraq, Iran, Saudi Arabia, Northern Africa, and Northern South America. As well as some subsidies going towards Asian countries as well. And this is to try to boost their own industry and make it more viable on the global market. So there's a lot of energy subsidies going around, and it's definitely not one country's problem. So the real downside as well is that while energy subsidies are often thought of a way of reducing the price to the consumer, so that, for example, you're paying less money at the gas pump. In reality, most of the energy subsidy money goes to the richest 20% of Americans. So the richest 20% of Americans get 54% of the benefits from natural gas subsidies and 61% of the benefits from gasoline subsidies. And so only a very small fraction, 4 and 3%, goes to the poorest communities. And so the benefits are definitely not proportional, and it's definitely evidence of structural inequalities within the system. So one of the most important things about reducing the amount of fossil fuel energy subsidies is that a lot of these oil producing projects would no longer be economically viable without these subsidies. So if we reduce the amount of energy subsidies, then nearly half of these projects would no longer be economically viable, and you'd reduce emissions in the US by 20% alone, just because there's no longer going to be as much extraction going on if these oil executives are not making as much money for these projects. So that's definitely a very important way that we can easily reduce our carbon emissions by providing that market incentive. So before we wrap things up, I just want to remind you all what are ways that you can do, things that you can do in order to address climate change. I know this topic can seem like a very big, vast thing that produces a lot of anxiety and stress in a lot of our lives, and I've definitely felt that myself, but there are things that we can do. One of the most important things is to vote. Get people registered to vote, and talk to your friends and family about climate change and make sure that they know that you care about this topic. Call your representatives. This is Frank Pallone, your representative if you live in New Brunswick. And so call them and make sure that they know that you care about this subject and that you want action on these subjects. Protest when you can. Donate as whenever you have money to donate to different societies, and reduce your carbon footprint. This is a societal problem and it requires societal fixes, but providing an example for others is a good way of starting the conversation and making sure we have change going on. So thanks everyone. In summary, for this lecture, we talked about carbon sequestration, geoengineering, energy production, carbon pricing, and subsidies, and lastly, actions that we can take to address climate change. So I really hope that you all enjoyed this class. I sure enjoyed teaching it and making these lectures for you all. Please email me with any questions you have about this material, and otherwise I will see you all soon for the final and the assignments to come. All right, thanks.